I want to get going. Are we going? Okay, apparently we're on the air. So, ladies and gentlemen, hello. Small class, but quality counts for something. Good to see you here. So today we're going to talk about object interaction. So far all of our work has been based on just making one object and making that object do something. Now we're going to talk about how we make systems of objects. So because any real program is going to involve more than one object, and you're going to want objects talking to one another in some fashion and doing things with one another. So object interaction is the name of the game today. Excuse me. So let's start off with thinking about buying a car. If you go out and buy a car, you probably think about a car as the whole object, and you have this car or that car, and you have different kinds of cars that you might be interested in. And you make your judgment based on some feel or properties of that car, maybe on the color of the car, maybe on the fuel efficiency, maybe on the capacity, maybe on the noise the engine makes, if that's your kind of thing. So, but you're considering a car as an object, as a whole object, which is pretty normal. But of course, a car isn't just one object; it's made up of many parts. To be building our own car, we'd have to actually start to make some decisions about what those parts would be. And so we think about the car not just as the whole car, but also as the parts that make up the car. And so we might make a choice about what tyres we're going to have in the car, what engine we're going to put in the car, what chassis we're going to use, and what gearbox, and the other pieces that make a car. Of course, an engine isn't just a single object. An engine is actually made of many pieces. And so if we were to actually decide to make our own engine, well then we'd have to decide on what manifold we were going to use, what distributor, what radiator, what spark plugs, blah, 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 all the pieces of the engine. Of course, a spark plug isn't a single object. A spark plug is made up of many pieces. And so if we were a spark plug manufacturer, we'd have to decide what materials we were going to use for the side electrode and the center electrode, and what materials for the insulators and the casing and the various other parts of the spark plug. Of course, a metal isn't made up of only one piece, right? A metal has many parts. You can see where I'm going, right? Everything that we deal with in the real world, every object that we have, is actually made up of more objects underlying the thing. And when we're talking about an object, we generally treat things at a certain level of abstraction. So abstraction is the general idea that depending on what level of detail we're talking about, we can treat a car as one whole object, or we can treat it as a collection of parts, or we can treat the engine itself as a collection of parts, or we can treat the parts of the engine, like the spark plugs, as a collection of parts, or we can go down as far as, you know, the atoms that make up the metal, that make up the parts of the spark plug, or we can go down as far as the protons and neutrons and electrons. So every conversation that we have about a car will exist at one of those levels of detail, or maybe between a couple of levels of detail. So we might talk about the car as a whole and the pieces that it's made up of. But generally we won't talk about, when we're talking about making a decision about buying a car, we won't talk about what atoms it's made of. And I like this car because it's got more iron atoms, whereas this car has more aluminium atoms in it, or something like that, right? So every conversation has an appropriate level of detail. Abstraction is the idea of knowing what level of detail to talk about at any particular time in your program. Now, in the end, your program has to get down to those atoms. Every program has to get down to talking about the individual numbers that make up your code and how you're moving them around. But when you're writing your code, you don't want to start at that level. You don't want to start by talking about all the numbers that are involved in what you're doing. You want to start by talking about the big picture objects, and how those big picture objects are made up of smaller objects, and how those smaller objects are made up of smaller objects, and so forth, right down to how the smallest objects are made up of individual numbers that make our code. Right? So everything we've looked at so far, we've made an object out of the most primitive types. We've made it out of numbers, and in fact we've already used some other objects in our work. you may not realize it, but strings are actually objects, and strings are objects native to Java. And you can look inside the string class if you want and see how a string is made up of smaller parts. But we are able to ignore that and just treat a string as an object on its own. And so the advantage of this is that we don't have to worry about how a string is implemented. We just need to know that a string represents a line of text, and that we can do various operations on that line of text. We can print it out, we can pass it around, we can add two lines of text together. Now what Java's doing underneath is that line of text is represented as a whole bunch of numbers, but we don't have to care about those numbers. So the key idea of abstraction, and it's a very important one, is that we break down a large object into a bunch of smaller objects. And each object has a public interface which says, here is how you use this object. So the public interface to a car might be, is about, how the actions you can do with that car, driving that car, parking the car, various other actions. But then there's a private implementation of how that all works. And so inside the car, there's actually implementation details about what happens when you drive the car. How does it all, what's going on when you do that? But most of that is hidden from you as the user of the car. In the same way, when we write our code, we provide a public interface, which is how you use the objects that we create, and then private implementation details, which is how it actually works. And you've seen this already in the access modifiers we give to things. So we have public methods. They're the interface. That tells people how you can use the ticket machine, for example. But there are private fields. The private fields are how the ticket machine is actually implemented. That information is private to the ticket machine and not available to the public to know about how to use. So we've done that at one level of abstraction. We've had the ticket machine, we've had the outside world use the ticket machine as something you add money to and get refunds from. And then inside the ticket machine, there's a private implementation which involves keeping track of these three different numbers: the price, the balance, the total, and so forth. What we're going to do now is have multiple levels of abstraction. And so the outside we'll see the idea of a car. Inside the car we'll see an idea of the parts of the car. Inside the engine we'll see an idea of the parts of the engine, and so forth, right down to the bottom level where we'll talk about the actual implementation of a spark plug, for example. So this is crucial in order to build code that we can actually understand what we're doing. Once again, the computer really doesn't mind. You could write everything in one class. You could write your entire implementation of a car as pages and pages of Java in one car class. But that would be really impossible for anybody to make sense of or to actually work with. So what we do is by adopting different levels of detail in our discussion at different times, we can talk about things in a way that is much easier to understand and easier for us to actually reason about in our design. So we'll get into how we do that. But it's a very, very important idea. It's basically the idea that we can divide a complex problem up into chunks and treat each of those chunks as a sub-problem in its own, an independent sub-problem in its own right, solve each of those chunks, and then combine them together to find a solution to the original problem. And this is what we call abstraction. It's basically about making problem solving easier by choosing what level of detail we're going to talk about at any time. So rather than writing everything in the lowest level of detail from the outset. So to implement abstraction in our code, we basically are going to be creating multiple classes. And each of those classes are going to exist at different levels of the hierarchy of detail. So the highest classes are going to describe an entire car or something like that. Then that car is going to be made up of other classes which represent individual parts, which are made up of other classes, which are made up of other classes. And then at each level, each class is implemented in terms of the level below. At the bottom level of our hierarchy are what we call the primitive types. And these are the things you've already encountered. Int is a primitive type. Boolean is a primitive type. These are types that are basically, you can't, there's nothing inside them. They just are, like they're the atoms of our program. These are the fundamental units of what we're doing. And they really are, I mean, well, actually, if you looked further inside, you could find out that an int is actually made up of smaller parts still. But Java, this is the smallest part that Java lets you get at. When you start looking at the computer hardware, you'll find that an int is made up of a couple of bytes, and those bytes are made up of electrons on pieces of memory. But you don't need to worry about that. From Java's point of view, at the bottom of your hierarchy is an int, or a bool, or a boolean at least. Like I said, a string is not a primitive type. A string is actually a class, which is why we spell it with a capital letter, like all our other classes, and it's actually implemented internally in terms of ints and other things. But we don't need to worry about that. So the other important thing to know, to realize, is that classes are types. So we talked before about how we had, when we defined a variable, when we had the return type of a method, in other occasions we had to specify a type. Classes are types. So wherever before we could pass around a primitive type, where we had a variable which was an int, or a variable which is a boolean, now we can have a variable which is a ticket machine, or a variable which is a car if we have a car class, or various other things. In the same way, we can have methods that pass around classes as types. Yes?
Excuse me, what's the difference when you define a variable int or as an integer? What's the difference?
So int is the shorthand. Okay, so I'm going to use those words interchangeably. Int is the
precisely like int.
Yeah. So you shouldn't be able to, in Java you can't actually say it's an integer. Oh, you mean a capital I integer? Ah, right. Okay. That's a complicated thing. Oh yeah, all right. So that's tricky. Yeah, Java does something weird. I'll show you what the question is about. Let's just create something new in here. Oh, okay, you're going to give a class test. So we can create, so we can do private int variable. I'm going to just call it variable, and that declares a variable which is an int. We can also do private capital I integer v2. That declares v2 also as an integer. The difference is subtle. The integer class, the capital I, so the little I int is a primitive type. So it's just a primitive number that you can't look at. The capital I integer is actually an object that represents an integer. So really all it is an object where it has only one thing in it, which is a number. The Java is trying to be clever. This is basically so that you can treat ints as objects, and sometimes you'll want to do that. But I think you'll probably never encounter a situation where you need to do this.
It's not a reserved word?
So it's not a reserved word, but it is a class in the API. And so it's not read. Right? So later on, if you ever need to treat a primitive type as an object, you can use these capital I, integer, capital B, Boolean classes, but we won't be dealing with that probably in this course, so don't need to worry about it. So if we're ever going to represent an int, we'll just use the little I and t for an integer. Okay, good question though. Although someone's been reading ahead. And then, so for example, if we wanted to use, if we had our car class, and if we also had two other classes, an engine class and a gearbox class that we defined, then an example is we can use classes as fields. And so we could say that a car is made up of an engine and a gearbox, and these are variables, and the type of, well, they're variables, they're fields. The type of this one is the class engine. The type of this one is the class gearbox. And also I'm going to introduce here something, style thing. I always, they don't do it in BlueJ, but I always name my fields as my something. It just avoids confusion. It makes it easier to identify at a glance whether something's a field or a local variable or a parameter. Anything named my is a field. And so the reason I do that is that often you'll get situations like I don't know if any of you did it in your ebook reader, but if you had this, and then you had public, we'll have a test string author. Now we have a problem. We've got a field called author, and we've also got a parameter called author, and we want to say author equals author, and well, that's really not going to work. So one thing we could do is we could come here and say, well, we could give another name to this parameter, but really author is the best name for that parameter, right? So we could call it A, but then that would be losing readability. We could call it various other things. The easiest solution, the best solution in my opinion, is for all fields to be called my something, and then this becomes quite straightforward. This then says my author equals author. So then little a author is the parameter, my author is the name of the field. So I'm going to use this from now on because I reckon it's good style. It's not in the BlueJ style guide, but I recommend that you do it as well. It means that later on it's very easy to tell when I'm talking about a field. Anything with my at the beginning is going to be a field. Anything without my is going to be just a local variable or a parameter. So let's close that. So here's our car class. Actually, I'm going to go, okay. So I've started writing a class for cars. In fact, not only did I write the class for cars, I wrote 3 classes for engine, tyre, and gearbox. They're all empty, so they don't do anything yet. Oh, whoops, what happened there? Oh, BlueJ's just given up. Okay, let's try that again. There we go, it's back. Let's get rid of that. Remove. Yes, remove. So the car, so we can now define fields whose type, the type of this field, is one of these other classes. And BlueJ does something nice for us here, which is then it creates this diagram. It doesn't always create this diagram, which is a little bit annoying, but it's meant to create this diagram, which shows these dotted arrows are the users arrows. You can, if you hover over here, you can actually you can add a users arrow. This shows that the car class uses the engine class. In other words, somewhere in the car class, it has a field which is an engine class. It also uses the tyre class, uses the gearbox class. So these diagrams enable you to see how your classes are related to one another. So I think So what I said there, we have class diagrams which show how they're related to one another. Now this doesn't show that our car has actually 4 separate tyres. It just shows that the car class refers to the tyre class, right? So I mean, how it refers to the tyre class, it doesn't actually say, but at least it tells us something about how things are related to one another. A good class diagram represents the hierarchy of how things are of abstraction. So that here you can see the car is made up of subparts, and the 3 subparts are the engine, the tyre, and the gearbox. A bad class hierarchy is one where you start getting loops in here, where the engine has a car as well as the car having an engine, and everything gets rather tangled and messy. That's an indication that you've designed things poorly. A good design sort of starts at the top level of abstraction, and then that breaks down to the next level, which breaks down to the next level, and so forth. So now we have 2 levels of abstraction in our car program. Now here's a different way of looking at it. This is an object diagram. This actually shows if we created an actual car object, what parts it contains. And so if we look at if we come here and compile and create a car, and we'll call it car 1, we open this up, we can see that the car has all these fields, and all of the fields have this arrow in them. This means that this is a reference to another object. So the engine isn't actually, the details of the engine aren't actually stored in the car. They're stored in a separate object, which is the engine object. And if we double click on that reference, we'll find there's the engine object. It doesn't actually have any fields, but that's the object that's the engine. and each one of these refers to a different object. Now, it's actually useful. Unfortunately, BlueJ can't do it, but it's actually useful sometimes to draw these kind of diagrams that show how what objects you've created. So we've actually created 6, 7 different objects, and this is how they're related to one another. This one big car object contains the other references to the other 6 objects. So each of these fields on the car object points to one of these other objects. Now that idea of being a pointer is important. These arrows, it's better to think, rather than thinking about this as the car, each of these fields containing the object, think about it as the field contains a reference to that object, or an arrow pointing to that object. And the reason why that's important is sometimes we can have, for example, 2 different references which both point to the same object. So if my car has an owner field and a driver field, then we could have the owner and driver both pointing to me. I am a separate object. There aren't 2 copies of me, one here as the owner and one here as the driver. There is one of me and 2 references to me. The owner field refers to me and the driver field refers to me. The reason why this is important is I'll show you, is if we start doing assignments, we could say my owner. So we've got, here's me, here's Claude. We've got my owner, we've got my driver, and we've got my passenger. Right, and these 2 point to there, and this one points to there. Right. Now, these are variables like any other variable, and so we can do assignment with them. In particular, we could say my owner equals my passenger. Now what that would do would be to erase this arrow and then copy this arrow into there. And so a copy of that arrow goes like that. And now my owner points to Claude, is a reference to Claude. My passenger is still a reference to Claude. My driver is still a reference to me. And so the important thing here is nothing has changed about me by doing that, right? All we've done is the reference has changed. And so the owner is now Claude, but you haven't changed me. You haven't copied Claude onto me in some sense. That would be weird and kind of freaky. All you've done is changed the reference here to point to Claude instead. So we've changed in the way that if we did change the ownership of the car, it wouldn't change me in any way. It would just change who owns the car, right? So when you're trying to think about these things, drawing these box and arrow diagrams is a really good way to make your ideas clear, because when you're copying one variable to another, all you're doing is copying these arrows around. You're not actually changing the things that they refer to. You could actually even assign all 3. You could say my driver equals my owner, and then all 3 arrows would point to Claude. Nobody would point to me anymore, which would be very sad. And it would also be rather tricky, him being both the driver and the passenger, but there's nothing stopping that from happening, at least in our code at the moment. So these object reference diagrams are a really useful way of you making sense of what's going on. I've been writing code forever, and still when I get a little bit confused about what my code is doing, it's easy to draw boxes and arrows and work through the process of saying, okay, I assign this to here, so this arrow now points to there, and then here, then here, then here, rather than getting too messed up in what's going on. So if in doubt, draw a picture. It's my The other thing is occasionally we'll have no object. Occasionally one of these boxes will effectively be empty. For example, if we have no passenger, we need some way of representing that there is no object in that box. The way we do this is there's a special value called null, which represents, in a sense, nothing. And so we can put null in there, and that now means there is no passenger object. That is an empty reference, if you like. It's called a null reference. And this is useful because sometimes we won't want, for example, if we don't have a passenger, we can use the null reference to indicate there is no person who is the passenger at the moment. And the null reference can be copied around like anything else. And so if we now said my owner equals my passenger, it would copy null into here. And so that would also become null and so forth. So null is a value that you can copy around. So in this way, we start to build objects which connect to other objects. And this is sort of one of the most important parts of object-oriented programming, is that objects can refer to one another. So we want to actually make, now in order to initialize those fields, we need to actually be able to construct objects. So where we talked about before about writing constructors, and you know how to call the constructors from BlueJ, now we can start calling the constructors in our code. And so this new statement is the way we call a constructor in code. We can say my engine equals new engine. And new engine will construct an engine object and then assign that engine object to my engine. And so what we're effectively doing there is, where did I put that eraser? If we have, so when we, remember that I said when we create a field, it's normally initialized to a 0 value. When we create a field that's an object, it's initialized to null. So that's the default empty value for an object. So initially, when we first create our car, my engine is null. But then we start running the constructor, and we say my engine equals new engine. And so what that does is over here it creates a whole new engine object. It runs the constructor on the engine in order to initialize whatever fields are in engine, and then it returns a reference to that object, and so that reference then gets assigned to my engine, and so my engine now points to this new engine that we've created out of nothing. Wouldn't it be great to be able to just do that? Just say new engine, and there's suddenly an engine there. In code, we can do it, right? It's fabulous. It's the wonder of programming. We can do anything. It's so exciting to wave my hands around. So this calls the constructor, and so we have to have an engine constructor in order to be able to do this. It runs the engine constructor to initialize the new engine that we've just created and returns a reference to that engine. That reference, we can do whatever we like with it. In this case, we're assigning it to a variable, and so we're initializing the my engine field by assigning a new engine to it. So now we can actually, so a little aside, we can actually have multiple constructors. So let's go and actually create an engine class. Where is the, let's close that and close that. Here's our engine class. We currently don't have a constructor for engine, which is all right because we don't have any fields either, so it doesn't really matter. But let's assume that an engine has a capacity. So we're going to have an int my capacity, which tells us the engine capacity. For car people, I really don't know anything about cars. I'm just making this up as I go along. So then if we create a constructor, we might just create a default constructor like this, which says that if we don't specify anything, then my capacity equals 1600, right? Picking a number that might have something to do with cars. So this is a constructor. When we call this constructor, it has no parameters, and so it just automatically initializes my capacity to 1600, which might be a sensible thing to do as a default value. I have no idea whether that's a sensible default value, but I'm just picking it out of the air. But we might also want to be able to construct engines of other capacities. What we can do is write a second constructor which has a capacity as a parameter. And once again, I'm using the wrong There we go. And now we can say my capacity equals capacity. And once again, you see why I like naming the things my, is that we can have two variables with similar names. So now, this is kind of weird that you say, well, how does Java know which constructor to use? If we give it two different constructors, what's going to happen? Well, if you come out to BlueJ, so if we compile that and come out to BlueJ, when we try to construct an engine, now there's two options. We can construct an engine like that, and that engine will have the default capacity, or we can construct an engine like this and give it a much bigger capacity, huge engine, and that engine will have our huge capacity. That must be like a space shuttle engine or something. So we have a choice in BlueJ. That's easy enough. But what do we do in our code? So here in our code, we were constructing an engine, and we said new engine. When we do it like this without any parameters, it calls the constructor that doesn't have any parameters. If we actually added a parameter in here, if we put in 2000 in there, Java is sensible enough to say, okay, that doesn't match the first constructor. The first constructor has no parameters, but we've tried to call it with some parameters, and so we're going to use the second constructor, which has a parameter. And so now, if we compile that and create a new car, there's our car, and if we check out the engine in that car, that engine has capacity 2000. So essentially, we can have multiple constructors, and we'll encounter this from time to time. Usually, you have multiple constructors because one is the default constructor, which has the sort of standard values for variables, and then you have later constructors which allow you to specify more information. And most of the classes built into Java are like this. If you just created something with a default constructor, it'll set some default values for it, and you won't have to worry about any arguments. It'll just set whatever's sensible. If you construct something with one of the constructors with more parameters, then you get to choose what starting values you're going to use. So this is kind of handy because it means that we don't have to, every time we create a new engine, we don't have to specify its capacity. If 1600 is the most common value that we're ever going to do, then let's just assume that in the default case that's going to be what we do. So it allows us to set defaults and basically make our code simpler. So like I said, which constructor we use depends on what parameters we pass when we run it. And actually I probably am jumping ahead of myself about parameter passing, but when we call the constructor, inside the parentheses we have to specify the values that we want for those parameters. So we'll get more onto that when we deal with methods. It's the same for methods as it is for constructors, and so I'll refer back to this when we get to the methods slide. But basically, if there's no parameters in the definition, then there should be no parameters when you call it. If you have an integer parameter in the definition, then we need to pass in an integer when we call it. If there are 3 or 7 or 8 or 2 million parameters, then we need to provide 3, 7, 8, 2 million parameters when we call it. Hopefully you won't be writing code with 2 million parameters. If you're doing that, you're doing something wrong. In fact, if you ever have really more than 5 parameters, you're probably doing something wrong. You probably need another level of abstraction in your code. Okay, so like I said, a method call. Okay, so we'll deal now with method calls. So we've made our objects, we've made our car out of the various parts of a car. But now when we want to do something with the car, we have to actually tell those parts to do what we want to do. So when we want to drive the car, we need to we want to start the car, we need to tell the engine to start, we need to tell whatever other parts of the car need to start when we start the car. So what we're doing now is actually calling methods. So the engine will have a start method. When we start the car, we want to start the engine first. The first thing we need to do is start the engine. And so we need to call the start method on the engine. So let's just do that. Let's add a start method to our engine. Here we go. Public void, because it doesn't actually return anything. Start. Proper syntax. And this does whatever, start the engine. I'm not going to go into the details. Whatever an engine does when it starts, I don't really know. Now when we have here, let's actually say the first thing we do if we want to drive, let's say that we have a drive method on the car. The first thing we want to do here is first start the engine. Okay? So in order to start the engine, we need some way of in code calling that method. So far you've seen how to invoke methods interactively in BlueJ. Now we need to start invoking methods in our code. So how do you do it? So a method call is going to be another kind of statement in our program. It's something that invokes another method and runs the method until it finishes and then comes back and keeps on executing the next statement. A method call, there are two different kinds of method calls that you'll encounter. They're very similar, but they have one important difference. Some method calls are internal, which is where it's where one method on a class calls another method on a class, on the same class. So they're internal, it's calling methods of the same object. External methods are where the one object calls a method on another object. So an example of an internal, sorry, yes?
Can we call, if it's a private method, can we call it from...
Oh, I'll get onto that. No, okay. So exactly, good question. So internal methods are just basically a way of, if we have inside a class, if we have code that we reproduce, that we write several times, it's usually a good idea to factor that into a private method, which basically means that if for example, in several parts of our code, so the example that we're using from the textbook is this, they had a clock. That clock has a display on it, but it also has a bunch of different methods for changing the time. One of those methods would be to set the hours on the clock. Another one of those methods would be to set the minutes on the clock and so forth. Now every time we change that information, we need to run some code to change what's displayed on the clock. Now rather than write that code in every single case, so when we set the hours, we write code to change the display. When we set the minutes, we write code to change the display. Whatever, we write code to change the display. Rather than having that same code in several different places in our class, we factor it out, which means we take that code and stick it into a method all on its own, and then that can be a private method. In other words, it's a method that's internal to the class and nobody else needs to use it. And so then whenever we set the hours, we can set the appropriate thing and then update the display, and it runs that update code. When we set the minutes, we set the minutes field, and then we run update display to run that code to update the display. So the idea is to take code that we use repeatedly and write it in a single method so it only exists in one place in our code. Yes, that question?
So just in that previous slide, so you have another class external to all of that with captures on wheel. So
yeah, so this would all be part of one class. Yes. Sorry?
So when you've got the bigger class outside, like on top of all of this, and then if you have another big class somewhere else, that can't talk to this.
So let me actually write something to show you what this looks like. So first of all, this is just internal to one class, right? So if we had, let's go and write an example of that clock class. Let's just do it here. New class, clock. So we have private my hours, int my hours, and we have private int my minutes, and it's spelled int wrong, and we have, I'm not going to make a constructor, but we have, and then we also have private string my display, right, which is the going to be the string that we constructed out of the minutes and seconds. Now if we had a public method, which is public void set hours, int hours, my hours equals hours. Right? Now that we've changed change the hour setting of the clock, we need to, yeah, I know I have a tute, go away. We need to actually update the display, and so we need to again say my display equals my hours plus colon plus my minutes, which is a really sloppy way of doing it. It would actually, updating it properly would probably take several more lines of code to update that, to make it, to pad it out with zeros or put an AM, PM or whatever on it, right? Now if we were going to set the minutes.
Excuse me.
Yep.
Does the compiler change the integer to string?
Yes, okay, so that's a, I think I said that before. Oh yeah, okay. So here, so here's something that I was being a bit coy about. Java is smart enough to see that this is an int, but this is a string, and this is another int. If you add something to a string, you always get a string. Java is smart enough to work that out, which is kind of handy because it means that we can make strings on the fly rather than having to actually turn my hours into a string. I was hoping to elide over that without anyone noticing, but well done. So, you know, and then we might also have public void set. Well, anyway, we could have several different places in which the this is not my hours. This is now my minutes. Minutes equals minutes, and this is minutes. This is copy and paste disease. Copying and pasting your code is generally, while it saves time, it leaves you making mistakes because you always forget to change the last things that you need to change. So what we've got now is this same piece of code. That line of code is there and there. Now, for example, say we wanted to change the way this was displayed so that rather than using a colon in between hours and minutes, we used a space, for example. So I'd come into my code and try to find where that was done. I'd find this spot here and I'd change it like that. And I think I was done because I changed the one that I could find. And I'd run my code, and sometimes it would appear with a colon and sometimes it would appear with a space, and I'd get confused, right? And the reason why is because we've got the same piece of code in several places in the source. And so it's easy to get lost and and think you changed everything when you've only changed the one spot. The way to do this well is to cut that out of there and actually write it in a separate method. So we're going to write a separate method here, which is void update display, which we call whenever something changes, and that does that, right? And line it up nicely. And now, where we ran the code before, we'll just call update display. And where we did it down here, we'll also call update display. And now if I want to change, if I change this part here, it changes it in every situation because we're calling this method. So we set the hours, we change the number, and then we run this method which changes the display. We set the minutes, and then we run this method which changes the display. So this is also a kind of abstraction. It's saying this method, there's this part of this method that we repeat all the time, or part of all these different methods that we repeat all the time, so we're going to take that out and call it a unit of its own and give it its own name. And so we give it a name, we call it update display, and we centralize that piece of code. And so now any changes to that piece of code will affect this and affect this and affect everywhere else in the code that we call update display. So if having repeated code in your program is generally a sign of bad design. If you have pieces of code that are repeated, or pieces of very similar code that are repeated but have slight variations, then you should think about factoring that out into a method on its own, perhaps with some parameters to allow for those variations. It'll make your code easier to read, it'll make your code easier to maintain. It won't affect the correctness of your code because Java doesn't care. But once again, it all comes down to making your code readable for other human beings. Good style. So factoring out common pieces. Basically, if you do anything more than twice, then it should be in a method on its own. It's very much likely to be the case. So the other thing I did here was, because this is a piece of an internal method that is only meant to be used within this class, we made it private rather than public. So anything that's private is the internal workings of the class. Anything that's public is the public interface of the class. So public things are available for other people to use, private things aren't. And in fact, you should be able to, if we compile this, and if I create a clock, if BlueJ is doing the right thing, I don't have access to that method. Right? I can set hours, I can set minutes, but I can't call update display because it's private. So if you're an external thing, you can't access those things. Oh, I didn't realize I didn't have that screen on. Oh well. People over that side of the room, I'll turn it. Hey, it's meant to be on. What happens if I press that button again? There we go. Good. It says it's on. There you go. Everyone can. I'll turn this one off, and you can all look over that side now. How about that? You can play tennis. Or back on again, or off again. What? On, off. Who cares? It doesn't really know. Good. All right. So these are internal methods, and internal methods are private, which means that they're only available internally. And to do an internal method call, you provide the name of the method, and then in parentheses, which is the round brackets, you provide the parameters to the method. So the one that I just showed you didn't have any parameters, and so we just had an empty pair of parentheses. But if we have parameters on the method, we have to provide the values for those parameters in there. And this is a comma-separated list. Sometimes some confusion people often make is to mix up their commas and their semicolons. Commas in method parameters, semicolons at the end of the line. So semicolon is a terminator, it's the end, whereas a comma is a separator. It's for separating items in a list. I'm afraid this is just the black magic of Java programming. Every computer programming language has these little punctuation things going on, and you just have to learn to get the right punctuation, because if you get it wrong, Java will not understand what you're trying to do. When we call a method, we have to provide values for each of the parameters, and those values have to have types that match the method parameters. So example, if we had this method which says it's meant to say something, it has a string that is a message that we want to say, and it has an integer which is how loud we want to say it, for example. Now the correct way to call this would be by passing in a string value first, which might be hello, and an integer value second, which might be 1. They don't have to be pure values though. We could also use expressions to calculate those values. So we could pass in the string hi and the expression 3 times 5. And so when we run that method, the second parameter will be set to 15, right? So when we run a method with expressions in there, the expressions are calculated first, and then the values are passed into the parameters. We could also use variables if we wanted. If we had a string variable, name is Malcolm, and an integer variable, volume, which is 4, we can pass in those. So any kind of expression which gives a string here and an expression which gives an integer there is any way of computing those values is a valid way of calling this. Incorrect ways of calling it: if we forget a parameter, it won't work. And so we can say hello, but if we don't have a volume parameter, Java won't like that. We can't put them in the wrong order, Java won't like that. And we can't pass things that aren't the right type. And so if we try to pass in true as a parameter, Java won't like it. We first have to convert that true into a string and then pass that string in, if that's what we want to do. The rule is that always the values that you pass in have to match the types of the parameters that are in the definition. And just enough time to get onto this thing. I said that they're private for access only. External methods then. We can use external methods to perform actions on other objects. And so the public methods can be accessed externally. Private methods can't. So if we have an object, which I've just called some object for a really clever class naming, we can call a method on it like this. It's the same syntax here where we say method name and then in parentheses the parameters, but the difference is this. Here's the name of the object that we want to call the method on. So at the beginning of the statement, we have the name of the object, and on that, and then we execute, and then there's a single dot, a full stop in between the name of the object and the name of the method that we want to call. So for example, if we go back to our code over here, we have the car. The first thing we want to do is start the engine. We can take the myEngine field, which contains the engine, dot start. Right? And because over on the engine class we've defined a start method, hopefully, somewhere. Here on the engine class we've defined a public start method. We should be able to actually compile that code and no syntax errors, so that the first thing we do when we try to drive the car is start the engine. And it'll run that method, do whatever start the engine does, and then return, and then it'll come on to the next thing that we want to do, which might be, do something with the gearbox or whatever. And so we were able to describe, the advantage here now is we're able to talk about what driving is just in terms of actions that we're doing on the fields of a car. So the first thing we do is start the engine. The next thing we do might be put the gearbox. We might go my gearbox dot select gear 1, right? And so forth. And that would be another method on this. So we're able to describe driving a car at a high level of detail. At a low level of detail at least, where we're just talking about abstract things. We don't have to go into the details about what's going on inside the engine when we start it, or what's going on inside the gearbox when we select a gear. That detail is hidden within the engine class. And so the engine class would now have the details of what happens when you start the engine would be written in here. So this means that we can look at, when we're just driving the car, when we're talking about driving the car, we can just think about it in terms of those parts and actions that we're performing on those parts. And we don't have to worry about what's going on inside. The last thing I want to say is that when we have a return value on a method, we can also use a class as a return value. And so, for example, oh, sorry, no, that's not what I wanted to say. We can use a class as a return value, but that's not what I want to say. We can, if we have a method that returns a value, we can use that method as an expression. So if you remember our ticket machine, we had a getPrice method, which was the accessor method that returned the price. So this method returns an int. We can now take the value we can call that method, get that int, it returns a value 100, we can then assign that value to a price variable. So any method that has a return value, we'll actually call a function. And we'll go more into the difference later, but a function, an accessor method or a function are different names for the same thing. It's something a method that gives you back a value. So an accessor method can be used then as an expression in a calculation. And so, for example, we could assign a value, assign that return value to a variable. Or we could have it as part of a larger calculation. So we could say machine.getPrice multiplied by 10 plus 7. And that would be 1007, right? Or whatever. So if a method has a return value, we can call it and get that value back and use that value in our calculations. All right, so that's objects, how objects talk to one another. That's the very basics of it. You should now know enough to actually do the entire assignment, at least for the COMP1400 assignment. The last thing I want to say is I'm going to be doing, so Claude has set up consultation times for Infosys, and I don't know what they are offhand. Hopefully he's published them on the blog. I'm going to be doing consultations next week for COMP1400, which I will do in the hour after the lecture. And so consultations will be here. Not here as in the room, but here as in COMP1400 consultations. And they will be, the location will probably, I'm not quite sure, probably the K17 building, level 4 meeting room. I'll publish details on that later. The K17 building is the computer science building. It's down behind MEcEng. So if you have any questions about the COMP1400 assignment, you can come and talk to me at that time. Thanks all for coming. See you later.